in the Milky Way, as I mentioned, there's 100 million black holes. All of them are a few times as heavy as our sun. There's a black hole in the very center of the Milky Way that's 4 million times heavier than our sun.
I'm here with Dr. Imre Bartos. He received his PhD from Columbia University, where he subsequently remained as a lecturer and then research scientist before joining the faculty at the University of Florida. His broad field of interest is multi-messenger astrophysics, and he primarily studies extreme cosmic processes related to the information and evolution of black holes. Dr. Bartos is a member of the LIGO Scientific Collaboration, the LISA Consortium, and is an associate member of the IceCube Collaboration. Additionally, Dr. Bartos is the Chief Technical Officer of Fire Neural Networks Company.
Correct. All correct. Yes.
Perfect. Yes. So yeah, thank you for coming here. Maybe we'll start with the physics side. That's why you're primarily focusing your research. So maybe we can start very broadly, like why physics, or what do you study primarily? What is your focus? I kind of gave it away already, but what is the thing driving you to wake up and figure things out of what's going on in the world and understand the world?
Yeah, so the point of research in general is to discover something that's nobody has known or seen before. Mm-hmm. And in physics in particular, this often comes with exploring the extremes and exploring the boundaries of what we know. And there are many directions to do this, but in my mind, the space and the universe itself is one vast area where there is plenty to explore, plenty of new directions or extreme processes that are different from what we experience down here on Earth. The less we know about them, the more there can be of a surprise, something that's beyond what we understand currently. And so space is, in this direction, very interesting. There's lots of things we don't know about space, but even more so are black holes, unknown or not understood. Mm-hmm. They are extremes in many ways, and extreme always means that something works differently than what happens down here. They are extremely massive, extremely dense compared to what we're used to. Gravity plays a very different role in their lives than in our lives, where general relativity is actually applicable as opposed to our Newtonian version of gravity. They also happen to, for example, accelerate particles to 1 billion times higher energies than what we can achieve down here on Earth. So for many, many reasons, they are extreme. And so we can test things, we can learn things that are not available, not achievable down here on Earth. And this is why I'm really interested in studying them and understanding them as much as possible.
Okay. Maybe we'll start with the black holes then. Like, what is it? Because I think people have definitely some idea, like some point supermassive or super dense or something that, like something that sucks everything. That's kind of like the popular understanding of it. Is there any insights into what exactly is it? Maybe a bit more technical, but just getting the intuition of what is it, right? Yeah,
so the name black hole by itself is actually a misnomer. It's not, we're not talking about an actual hole in any way. Maybe the way you can imagine a black hole is it's a sphere. It's not a hole. It's a sphere in space that is special only because it has such strong gravity that nothing can escape it, not even light, which is why it's called black. And so there's this point of no return, which is the sphere. Once something enters, it cannot come out no matter what. And so this volume, this sphere in space is what a black hole really is. Now, to put this in perspective, gravity is such that if you move farther from something, gravitational pull will be weaker. And so if we stay far enough from a black hole, it will behave just like anything else.
It will
attract, right? Exactly. So if the sun, for example, turned into a black hole, it will be dark, right? Not be pleasant, but otherwise our Earth would be rotating exactly the same way around that thing as it is now.
Right. So having conserved the same mass, just putting it basically as tightly compressed as possible.
It would not make a big difference. Exactly. The size of that black hole would be the size of Gainesville, so it would be very small.
Right. But like the diameter.
Yes, the diameter would be very small. But for any practical purpose, from a distance, they would behave just the same way. The difference starts to manifest when you get close enough to a black hole. So that very, very strong gravity starts behaving differently than otherwise. So, if we get really close, things will basically not just sucked in, which is sort of the sort of classical way to describe them, but effectively these black holes attract things and can collect matter around them. Now, part of it is that it's strong gravity nearby, but I think a bigger part almost is that they can get very heavy. So when we think of what else can be heavy in the universe, a star, for example, a star can be, maybe a few tens of times heavier than our sun, but not much more. They don't come in any size, basically. While a black hole can be a lot more massive than what we have for the sun. So there are black holes out there that are 10 billion times heavier than our sun. So there's a huge difference there. These are called supermassive black holes. And so that's a large difference. And that really is the reason those black holes will affect their environment very differently than, for example, a star. Now, with the strong gravity nearby, there can be other interesting phenomena that we can study. So once things are sucked in, that's one thing. But even before that, as things are approaching the black hole, they are accelerating, just like, you can think of it when a space shuttle, for example, if it still has some, entered the atmosphere, it heats up, and that's one of the things they have to protect the space shuttle from, this heating up because of the fast movement of the air. And for a black hole, something similar happens. If things are falling towards it, they accelerate, they move very quickly, there's going to be this friction. And so the gas or other material that's falling towards the black hole will heat up, and this heat will produce all sorts of interesting radiation that we can study, or it actually turns out that this heating and the ensuing outflow actually accelerates particles the same way, or in a similar way we accelerate particles down here on Earth. But because of the sheer size, the sheer energy of these black holes, this acceleration can be a lot higher, a lot stronger than what we can achieve down here on Earth. Again, it can be 1 billion times higher energy that these particles reach, which is still roughly the speed of light, but still the energy is a lot higher than what we can do down here on Earth. So it's not just when you fall into the black hole, but even as things approach the surface, things get very different, or rather things heat up, and these black holes actually, or their surrounding, radiates, and we can observe them very, very far. The farthest things we see in the universe are actually black holes with eating some matter from their environment. We can see them really, really early, billions of years ago, so we can see back in space and time, if you will.
Yeah, well, now we're getting a lot of concepts in. It might be a big flow of information, but we'll get into let me rephrase what you said to see if I got it right. So we have the black hole, right? And what you're saying is that, let's say a cloud of, you can think of it as like a cloud like we have in the atmosphere, right? Like just a gaseous form of particles going and falling to the black hole because it has gravity, just like Earth. And as we're getting closer to the black hole, gravity increases, just like Earth. Like if we're very far off the Earth, we're not really as affected by it. But as we come closer, we're starting to speed up because gravity becomes it increases. Therefore, we start to speed up. And as the gas starts speeding up, it starts having friction within itself, basically. It starts just colliding with itself, just a bunch of heat and light coming out of that interaction. And since it's going that fast, then we can see that interaction happening from very, very far distances. That's what you're saying. How can we see that interaction? Like what happens in there that we can somehow understand what's going on very, very far away in here on Earth? Yeah.
So first of all, exactly what you said. For detecting this radiation, there are two directions, I would say. First of all, just because there is so much matter typically falling in there is so much energy released in this process when matter falls into a black hole, they're going to be a lot brighter than other things that we're typically used to. So they often outshine whatever else is around them, many stars, for example. And so simply with our optical telescopes, we can see these black holes very, very far, simply because they are brighter than other sources of light in the universe, like stars, like galaxies often. But there's another way, which is connected to the accelerated particles that I mentioned, because when you have these much higher energy particles, they also interact and create radiation, which is going to be less what we detect with our eyes, for example, which is light, but rather photons that are much more energetic. They're called gamma rays. So with this very high energy particles that a black holes produce, they will emit gamma rays. And these gamma rays are something which is not produced by typically by stars or down here on Earth. They are very energetic, and so they are much more rare as a information that's traveling or produced in the universe. And so we can detect this very far, partly because we don't have other sources, and also because the way we detect these is in some ways easier. We can have gamma ray telescopes that are typically satellites that can see the entire sky and see any of these emitted gamma rays from all directions. One interesting case when this is especially detectable and bright is near the time when some black holes are actually formed. We talked about what a black hole is, but we didn't talk about how they come to exist exactly. Yeah. And so the main channel we believe black holes are formed in the universe is through the death of stars, of very large stars. And what happens is you have a star that's much more massive than the sun. The sun will never become a black hole. It's too light. So when it's spending its billions of years, it will basically eventually run out of fuel and basically shrink into what we call a white dwarf, which is going to be something like the size of the Earth. This is for the size of the sun. If a star is much bigger, say 30 times bigger than our sun, then it's going to be hot enough in its center so that it can not only fuse hydrogen, which is the main source of energy for the sun, but can also fuse heavier and heavier atoms, helium, carbon, oxygen, etc., all the way to iron. Iron is the heaviest element that can be formed through fusion. And this, first of all, creates a lot more energy. Second, the end result of this process will be that these massive stars accumulate a lot of iron in their center. Because iron is heavier than the other byproducts of fusion, they accumulate in the very center. They just sink into the center of the star and accumulate there. And imagine that these massive stars produce a big iron core that's about the mass of our sun. So there's going to be one sun worth of iron in the center of this much bigger, much more massive star. And at some point, this iron core will be so heavy that it's actually not going to be able to support its own gravitational pressure, and it will collapse. It will collapse into, it can collapse into different things, but one of them can be a black hole if it's heavy enough, especially with the rest of the star collapsing onto it. Now, first of all, this is how a black hole is formed. But second, as this process happens, not all the star will fall into this black hole right away. In fact, a big part of it will be carried away through a violent explosion that's called a supernova explosion. That basically is fed by this gravitational pool that releases energy, explodes some parts of the star. So the black hole's formation will often come with a ginormous explosion called a supernova. And this is interesting first because we can see these supernova explosions fairly often. So we can detect them far away. They are extremely bright. But also, when these black holes form in the center of these exploding stars, not all the matter that's in the star will be carried away by the explosion. There is going to be a fraction that will eventually fall back onto the black hole. And so there's going to be this fast feeding process when you have a few seconds when the newly formed black hole actually is fed a lot of gas from the star that was nearby, or the dying star. And this will release a very, very bright burst of gamma rays, which are called a gamma ray burst, just because it's a burst of gamma rays, which we can see extremely far in the universe. Again, we can see this billions and billions of light years away. They outshine the rest of the entire universe in gamma rays for a few seconds when they actually happen. So they are extremely, extremely bright. Their energy releases as if you took the sun and turned it into pure energy and just released it in gamma rays. It's extremely bright. And so we can see them extremely far. And the good thing is not just that it's very energetic, but also, again, as I said, you can see gamma rays with detectors that see the entire sky at all times. So you don't need to point your telescope in a direction. So it's easier to actually find them. In fact, this is how these were first found. The first identification of these of these gamma ray bursts happened in the 1960s.
Okay.
Because other than black holes that are accreting, there is actually another source of gamma rays, which is nuclear explosions in general. And at the time in the 60s, there was a proliferation of nuclear arms on Earth. And so different governments, including the US, wanted to put an end to this. And one way to do this was to monitor the other side during the Cold War, that they're not doing anything naughty. And the way they did this, the way the US did this, is sent up a network of satellites called the Vela satellites to monitor gamma rays coming from undeclared explosions of nuclear arms. And because there was no clear understanding of where these will happen, right? If you only monitor the ground, they may be exploding in space. They monitored everything, which was, again, not that hard because gamma ray detectors can see in all directions. And it turned out that there were these bursts of gamma rays that they saw, and they first weren't sure whether it's the Russians or someone else.
Okay.
But it turned out, and you know, they didn't know for a while, and it was also classified. So they didn't do much with it until about 10 years later when they ended up publishing it.
Okay.
But it was, again, classified for a long time. The article was called something like gamma ray bursts of extraterrestrial origin or something like that. So we have no idea what this is.
Right,
but
which is funny, right?
Because
It's basically like a satellite waiting for a signal of specific light amplitudes of like specific energy that we know because we've tested nuclear bombs and we know that nuclear bombs emit this kinds of radiation.
Yeah.
We had no idea that they were emitted in the space, and suddenly we were detecting them, and they're like, wait, what the heck is this?
Yes, luckily they didn't get too scared. They just didn't know what was going on. Even then, for a long time. So this was in the 70s when they could. So the satellites went up in the 60s, but they published this in the 70s. And even then, for a long time, people didn't understand what was actually the origin of this. They were so powerful that it was hard to imagine that they had come from very far, because what could possibly produce this much energy? And so it took basically until the 1990s. Even in the 1990s, there were serious discussions between scientists about, okay, is this something nearby? Is this something very far? It was not clear. And it basically only became clear that these are extremely strong, extremely distant bursts of gamma rays, and it turns out black holes, when we could see them from. So the first indication was that they come from all directions, not just from the Milky Way. But then the fact that they identified these from specific directions of distant galaxies was the real clue that, okay, this is really coming
very
from
far.
A galaxy far, far away. Exactly.
Yeah, and that's funny because I imagine for a period of time, do you think like people were not really aware of, not necessarily also how far they were, but also the origin of like what really caused them? Probably there was some wild speculation. It's like maybe messages from somebody telling us like, or exploding bombs nuclear bombs in other planets.
There were wild speculations, exactly. People didn't know. And even when we realized that these were extragalactic and they came from a long distance, it was still unclear what they actually were. So this was a very long process to come from, we had no idea, to, okay, these have to be very strong, very far, to, okay, this is the actual process that produces them. And the way we eventually learned what produces these gamma ray bursts is actually, it turns out there are two different sources for them. But it was, for one category, the identification of a supernova explosion, the explosion of a dying star from the same distance, same direction, same time as we saw the gamma ray bursts. And that was like, okay, this same event, same cosmic event has to be doing the same thing.
Okay, so you like visually see the explosion like with visual light.
Yes.
And you also detected the gamma ray burst. So it's like, oh, they should be coming from the same event.
Same direction, same time, exactly. It turns out that's only one of the two types of astrophysical processes that produce gamma ray bursts. The other one, interestingly, turns out to be also connected to black holes. So here, again, for the first one, a star is dying, forms a black hole from the matter falling to the center. The black hole is eating matter from the star, creates the gamma ray burst. The second type is actually due to a different kind of death of stars. So some stars that are not as heavy as those that create black holes, but not as light as the sun, can create another dead object or compact, as we call it, object called a neutron star. That's a sort of intermediate form of matter. For the star, just pressure holds
still very,
the
very
size
heavy,
exactly.
but not as heavy.
Very
as
heavy.
black hole.
For a black hole, there's no, gravity is not overcome by anything. Gravity is the strongest. For neutron stars, it's a borderline case because it's also a neutron star is also from that star, but it's not heavy enough to collapse completely, and there the nuclear forces that are inside atoms are strong enough to halt gravitational collapse, and so you'll end up with
it's like pressure from
exactly,
within, right?
and so you'll end up with a so-called neutron star that's basically a gigantic atomic nucleus. It's built up of protons and neutrons, just like any atom or atomic nucleus. And but it's the size of our sun, so it's a little bit bigger. But the density and everything else is the same.
And the gamma ray bursts come from the star.
So you have this neutron star that's formed, and oftentimes when you have stars big enough to form a neutron star, they're going to come in pairs. Turns out big stars like to be in pairs for some reason, and so you often will end up with two neutron stars that are orbiting each other, and eventually, due to what we may end up talking about gravitational waves, these neutron stars end up circling toward each other and collapsing or colliding. And when the two neutron stars collide, then they will basically create this matter that's first of all heavier than what nuclear forces can halt and will collapse into a black hole. But during this process, not all the matter will be automatically inside a black hole. And whatever is still outside will fall in. And this fall in will create the same kind of falling in, heating up, radiating. And so we'll end up with the same gamma ray bursts. So you can have a gamma ray burst from a dying star, or you can have a gamma ray burst from two dead stars colliding with each other. So all stars, all connected to the eventual formation of a black hole.
Yeah, and those two neutron stars are not necessarily dying, right? Like they die in a sense, I guess, because they collide with each other. But
so at the end, you'll have one black hole, right?
Right. So
whatever you call death.
Exactly.
We already call neutron stars dead stars because in some ways, a star is not dead while it's still producing energy, right? Once it becomes a neutron star or a white dwarf, it stops producing any energy. There's no more fusion. So in this sense, it's dead because there's no production of energy. It's a matter of semantics to some extent, but a neutron star is considered a dead star.
So just very briefly then, inside the neutron stars, there's no fusion going on. So what is the pressure that keeps the matter
nuclear
in there?
Pressure. So nuclear forces that keep matter from falling further. So the same force that keeps an atom the size of an atom.
Yeah, gotcha. Okay. So you mentioned gravitational waves. Maybe we can start heading to the direction of your TED Talk, which is fascinating. It was pretty awesome, pretty interesting to hear. It's basically like using multi-messenger information to get a better idea of what's going on in the space. So we've already talked about, we can see visual light, like we can see like the electromagnetic waves, which is light, and all its forms, like the gamma rays that you were talking about. But what other information can we get from space to understand what's going on there, and how is that useful?
Yeah. So first of all, what's wrong with just light? The problem is that light comes from many things, but not everything. For example, when a black hole is not eating anything, it will not radiate. There is no light coming out from the black hole itself. And even when
it's black.
because it's black, exactly. But even most of the black holes that are around us, they will, even if there's some matter around them, they're not going to be eating enough to be observable through light. As an example, just in our own galaxy, the Milky Way, there's an estimated 100 million black holes. So they're quite common, right? And we only see a handful. We only know a handful of them. Basically, the only way we can see these black holes is if they have a partner star that's nearby and they are feeding off of. And then they can radiate enough that we can see them. But this is a tiny minority. We don't see most of them because they don't eat enough to be visible. So light is not really good for studying most black holes, for example. Also, if you just think back of what we discussed about the explosion of a dying star, a supernova explosion, basically, the way you can imagine this, you have this very massive star that has this iron piling up in the center as it's formed through fusion. And when this iron core collapses because of its own gravitational pull, it will collapse, and then it will basically pull the star in and pull some of the star into the collapse, the new black hole, explode the rest of the star. But this will happen only after a while. So for a long time, when this whole thing is happening, this whole violent collapse is happening in the center, the outside of the star will be as if nothing's happening. You don't have anything in light, at least, that's coming out from the surface that gives you information of what's happening inside. So there are many cases for these processes, including a supernova explosion, where light will not be able to come out from some dense environment, and so we will only observe the surface, which is not all the information that we could or we would ideally want to have. So light has limitations, and so what are our options? And here, the key sort of insight is that nature has 4 different forces, and each force comes with its own messenger or something that transfers that force. Exactly. And light is, and the gamma rays, all that we discussed is the electromagnetic force, which is one of the 4, right? So there's still other things out there. And another force in nature is gravity. And so gravity has its own messenger, although it's a little bit
hard to detect.
It's hard to detect, first of all, and it's also less theoretically clear, I would say, than the other ones. We don't fully understand how these forces are sort of
like the
are existing
theory behind it.
Yes, but basically, we know that gravity is there, and it turns out that with the standard way we think of gravity is that there is something big and it's pulling everything towards it. But it turns out that just like any kind of field, if you move something very quickly, it can create waves in this field. So one analogy you can think of is the surface of a lake, right? If you drop something in, if you move something quickly on the surface, you drive your boat, for example, it can create waves on the surface. And the same thing happens in gravity as well. If you have some heavy object that creates gravity, and you end up through some way moving this object very quickly, accelerating it more specifically, then it can create waves in gravity itself. And these are what we call gravitational waves, and they can actually be produced by black holes as well. So if I take a black hole, nothing's coming out of it except it still does have its gravitational field. So if you have a way to quickly move a black hole, it will create these waves of gravity or gravitational waves that are coming away from it, and we can use that to actually find black holes that we would not see through any other means. And this is what we are doing with what's called or what are called gravitational wave observatories, such as the LIGO observatory that I'm working with. And the key idea is really just this. When there are waves in gravity itself, we can detect this. Now, the trick is that when we think of gravity, it's a little bit more complicated than how we experience gravity in our lives. In particular, according to the general theory of relativity, gravity is actually the distortion of space and time. So in gravity, distances are a little shorter and time is a little slower than without gravity. And so when we have a gravitational wave, it's not just that there is some wave of how much you're pulled towards a direction, but it's actually a slight changes of distances that we can use as a way to detect these.
Right, so maybe like the analogy of the lake is a pretty good one in this sense, right? You have some medium, right, like a bunch of, like something that it's maybe static, maybe, if it's far away, and if you have that boat that passes through, that medium gets disturbed, and the waves start propagating through the medium, and you can see the waves. Like if you have maybe like some detector that feels that pressure, you can see that thing moving when the waves collide with it. And that's pretty much what we're doing, if I'm understanding
That's pretty
correctly.
much what we're doing. So again, gravity is changes in distances, and so all we need is a very precise ruler. We need to measure distances, and as those distances change with time, periodically, as you have a gravitational wave coming, that indicates what the wave is doing or where it's coming from. So we are really just working with a very precise ruler. Now, again, the trick is, and you mentioned this, that gravity is unfortunately or fortunately much weaker than the other forces in nature. So, when we think of rulers, right, millimeter, whatever, right, there are standard distances. The distance change. So the ruler we are working with, the LIGO ruler, is 2.5 miles in size. So that's, we need the bigger one to work better. And over this distance, the change of the distance between the two ends of this 2.5 mile ruler that we need to detect to find gravitational waves is what scientists call 10 to the minus 17 meters.
Right.
So the way you can imagine this is if you take a proton, which is...
There's probably no good way to imagine it,
There's
right?
no way. So one way to imagine is, right, like you have an atom, right? What is an atom? An atom is
very,
basically
very small thing,
some electrons, and in the middle you have the atomic nucleus. In a hydrogen atom, it's one electron, one proton. The electron is 10,000 times bigger than the size of the proton in the center. So it's mostly empty, but you have this tiny proton in the center. The proton is roughly 100 times bigger than the change we need to detect.
Okay.
So we need to detect the change over 4 kilometers.
It's like the size is between the proton size and the neutron and the electron size.
That's 10,000. But we need to measure a distance change that's a lot smaller than the size of the proton, not just the atom. So, which is in some ways counterintuitive because you have a detector built of atoms and you want to use that to detect something smaller than an atom, right? Kind of strange, but it turns out that it actually can be done, which is exciting.
By a bunch of really cool physicists, engineers working together, and
$1 billion of funding.
$1 billion of funding, yes.
Yes, and so this is what we do, and with this, we detect these fascinating signals called gravitational waves that are coming from black holes. Now, right, if you move a black hole quickly, it will create gravitational waves. But how would you do that? And it turns out the best way to move a black hole is by putting it close to another black hole. So the main source of these gravitational waves that we can detect, that's from moving black holes, is when two black holes orbit each other very closely and eventually collide.
The same idea as this neutron stars.
Same idea with the neutron
something
stars.
Orbiting and then coming closer, and then
eventually merging. Exactly. So they're getting closer because as they emit these gravitational waves, that basically is taking away energy from their orbit and making them get closer and closer, again, eventually merging. When two black holes merge, interestingly, they form one bigger black hole. So it still stays about there's a conservation of black holes in a sense. But that's the best way we can produce, or the universe can produce gravitational waves. And so we see many of these colliding black holes now in the universe. Now, we see, and many is also interesting because this was a very long process. The first time the idea of gravitational waves was mentioned was basically right after the publication of general relativity by Einstein. Einstein was looking for ways to probe this observationally, and one of the ideas
30s,
he had
40s, maybe.
That was 1916, so about 100 and a few years ago.
Yeah,
and so that was the first. For a long time, people didn't believe that this was reasonable, and even the existence of black holes was not clear until.
This was theoretical, but not.
Yes, so gravitational waves were theoretical for the most part. And then the existence of black holes was also theoretical until the 70s, basically.
Yeah, and the cool thing, just briefly, theoretical means we have this equation that describes what this thing is happening, and the equation tells us that this thing should exist, but we don't really know if it actually exists or not. But then eventually we found it.
It was even worse. Einstein himself did not really. He was not really sure whether this is something which is a mathematical quirk that will go away if you change the coordinate system, or if it's a physical phenomenon. So he wasn't sure for a long time, and basically we had to wait until the 1950s for this to be thought of as a real phenomenon that one could in principle search for, and that started a race, if you will, by several groups of researchers to build gravitational wave detectors.
Interesting.
But even then, this is, again, the distance changes we talk about that had to be detected are extremely tiny. And so even then, right, development started in the 50s. The first discovery of gravitational waves was achieved by LIGO in 2015. So it had to be another 60 years before. So it was a very long effort. And
probably you were saying the races, I imagine a bunch of the competitors ended up merging together efforts, and like a lot of the funding ended up combining, I imagine, or not really.
So it's there's a lot of details here
Right.
that are interesting.
A bunch of history.
There are different ways how one could, in principle, try to detect gravitational waves. Right, you want to detect small changes of distances. The method that we are using now is called an interferometer. That's basically using a laser beam to measure how long distance the laser beam has to travel by how much its phase changes, the light's phase. But there are different ways in principle, and the first detectors that were being constructed were basically large pieces of aluminum, and people tried to measure their resonance due to this distance change. It turns out that it's not as good a method, but for a long time, many groups were building those kind of detectors. In fact, there was a group that announced the discovery in the 60s, which turned out to be not true.
Right. Okay.
So again, it's a complicated and long
interesting. So it's like the resonance, like the vibrations within the aluminum
vibration,
pieces.
Exactly.
And you were okay, interesting.
That was the idea.
We can get into it.
Yeah. So it's a long story, but it took a long time, and it took a lot of courage by these people, because they really didn't. I think that the really fascinating thing is that it's not that they knew what they were looking for. They thought there could be gravitational waves in the universe, but they had no idea what may be producing that, right? Again, when this was starting in the 50s and 60s, people didn't know that there were black holes. Didn't know even more whether these black holes collide or do something that could produce gravitational waves. So it was completely unclear. They were out just in this wild goose chase, I guess.
That's pretty funny, and that kind of continues, not necessarily with the gravitational waves, but like all the phenomena, right? Like that we think exist, but we're not really sure. So we build this massive experiments and a bunch of money to just figure out if they're true. And I was gonna ask you about whether you think it's worth it, because a lot of people have that questions like, oh, a lot of money but if you can briefly comment it, like what for you is the motivation towards spending all that much effort and time and money into that endeavor? So
the money is not mine. So it's
right.
It's
but
the government's
it's
money.
In a sense, it's everybody's money, right? Like
right. So I think there are different ways to justify this, on a personal level or on a societal level, if you will. I think maybe starting with the personal level, I think many scientists are driven by discovering something that's completely new, right? People like to explore. People like to find new things in many different ways, and I think scientists just do this in a way where we read whatever is out there, and we want to find something that's not just new for us but new for everybody, which is kind of a fascinating thing, right? To expand knowledge for humanity in general.
And just that, it could be like the only reason that you could get, right? Because I was talking to Deshika Narayanan, the other professor here in physics,
I know him, yeah.
And I asked him kind of the same question. He said, well, first of all, like forget about like the usefulness of it and like how the many technology that comes out of it. Like, first of all, it's awesome, right? Like we're expanding what we know about how the universe exists and how we're here, how it all works, and that alone should be worth it, right? Like, at least you would agree with that, I guess.
So the thing to keep in mind is that for most of human history, this was not the case, right? So we live in this very interesting time where, for some reason, government supports this awesomeness, basically, for no clear reason, always, at least. But this is the exception. This is not the rule, right? So for a big part of human history, the science was supported by individuals who just wanted to have fun, and this is not always the case today, which is very interesting. But I think what we have to realize is that, despite this being maybe the motivation for to some extent for many scientists, that they are doing something that's cool and awesome, ultimately science is a very good investment to society.
And that's the other thing.
There are going to be a lot of added benefits, even if that's not always clear from the very beginning. So I think even from a sort of rational, I don't care about cool, but just want this to be useful perspective, it's actually an extremely good investment to support sciences. So I think this is in many ways very forward-looking, that science is being supported. And again, it's often, and in my case, almost never clear immediately what the benefit will be.
Right. Well, we can continue talking about big efforts. I'll ask you about the final two big collaborations that you're part of.
Yeah.
First LISA and then IceCube. So what is LISA? We've already talked about a bit about LIGO.
So LIGO is Laser Interferometer Gravitational Wave Observatory, and it's the first detector to have discovered gravitational waves in 2015, so almost 10 years ago at this point. And this is something where we built a detector on Earth, which is, again, a large interferometer shooting lasers into directions.
Big laser Where is it?
Sorry?
Where is it?
We have two, actually. One of them is Washington State. The other one is Louisiana.
Right. Okay.
And one of the key sources of noise that we are dealing with is the Earth shaking a little bit underneath. And so the idea is that this could be mitigated if we went to outer space. There's another benefit, that it's not just the Earth shaking, but another sort of cumbersome detail for building the detectors is air itself. Well, gigantic is, but more specifically because we need to be in vacuum.
Air is
in the way.
The vacuum.
Yes, so LIGO is actually the biggest vacuum on Earth, which is a meter diameter or so, 3-4 feet, and 2.5 miles in different directions. So huge vacuum, and it has to be ultra high vacuum. So for this reason as well, going to outer space sounds like a useful idea, because you can have a lot more of that vacuum without any significant effort. And so this is meant to be LISA, which is Laser Interferometer Space Antenna instead of Gravitational Wave Observatory. And so this is a planned, or now under construction, satellite network of 3 satellites that are going to be launched next decade, so in about 10-ish years. And they're going to do the same thing, except it's going to be a detector which is a lot longer. So instead of a few thousand feet, it's going to be more like 1 million miles, basically. So a lot bigger.
Oh wow! And, so you said the length of the arms in LIGO is like 2.5 miles, something like that.
Exactly.
And LISA would be
about 1 million miles. More than 1 million miles. Yeah. So it's a big difference.
A good amount of increase, right?
Yeah. And so this is good for sensitivity, but also it turns out that for much bigger detector distances, the black holes that we're looking for can also be much bigger. So instead of looking for the black holes that are colliding that were formed from dying stars, what we mentioned, which is roughly the size or a few times more massive than our sun, these space-based detectors, LISA in particular, can look for the collision of not these smaller quote-unquote black holes, but the collision of supermassive black holes. We didn't talk about supermassive black holes other than that there are these very heavy ones. It turns out that in the center of basically every galaxy, there's one black hole that is a lot heavier than all the other black holes. In the Milky Way, as I mentioned, there's 100 million black holes. All of them are a few times as heavy as our sun. There's a black hole in the very center of the Milky Way that's 4 million times heavier than our sun. And in most galaxies, there is one such black hole in the very center. And occasionally in the universe, galaxies collide, and the black holes in their center collide as well. And this can be detected. However, we cannot detect this with LIGO, but we will be able to detect this next decade with LISA. So that's the difference for LISA. And IceCube is a very different option again. This leads us back to the 4 forces that I mentioned. We can have different information collected from the universe through messengers carrying the different forces. And we talked about light, electromagnetic force. We talked about gravity, gravitational waves. There is also what's called a weak force that we don't experience in our own lives for the most part, because they only operate inside atoms. But they actually are carried mainly by a particle called a neutrino. A neutrino is a very, very tiny, very light particle that's neutral, doesn't have any electromagnetic or electric charge, but it's interacting with its environment through what's called a weak force. And so detecting these neutrinos tells us something different about the universe. And also, it's not just the force itself, but also these neutrinos, as the weak interaction, as the name implies, interact very weakly, which in practice means that they can travel through dense matter, for example. So as I mentioned, when we have these dying stars, we don't see what happens in the center because light cannot escape. However, neutrinos can. And if they are produced in the center, they're going to come out and carry information with them about what just happened inside. And so this is something that can be searched for differently, and because it's a weakly interacting particle, the detection is also more difficult. And this is where IceCube you have to be creative a little bit, and this is where IceCube comes in. The idea is that there's very small chance that a neutrino will interact with a piece of matter or a detector. So you have to build as big of a detector as you can. And the way IceCube achieves this is by not building a detector, but by using ice at the South Pole specifically as the material that will do this interaction for it. And IceCube basically uses a cubic kilometer worth of ice there, which is actually very pure for some reason, at the South Pole, and monitors basically any interaction that happens within this cubic kilometer through different modules that are dug inside the ice. And this is able to detect neutrinos coming from outer space, again, any point basically of the universe that are very weakly interacting, and so they can escape from places where light cannot. And just to give you an idea of this weak interaction, it turns out that when you have this detector at the South Pole, the best way you can observe these neutrinos is when the neutrinos cross the Earth, because many of them do. The Earth is not a problem for the neutrinos. They can easily cross the Earth, and that filters out any other signal that might be bothering or might be producing a background. Also, just as a conceptual example for the weakness of neutrinos, if you just take your finger, right, every second there's 100 million neutrinos passing your finger every second. So it's quite a few neutrinos that are around us, but they don't interact.
Feel it. So
exactly.
That's why the detection of we can actually measure that they're passing is very difficult. That's why you need this big effort of this big detector to get that weak interaction.
Yes.
Okay, so we're running out of time, so we'll switch completely. We've talked that you're, of course, a professor in the physics department and doing all this amazing research in physics, but you're also, as I mentioned, part of a company. Like, you're the chief technical officer of Fire Neural Networks. So what is it? What is Fire Neural Networks? What are you trying to solve? And what are the cool aspects of, so why are you taking the time of doing all this cool physics thing? Why are you also taking time to do this endeavor?
Right. So you mentioned briefly that science is interesting because it often doesn't have a direct benefit to humans, and one of the things that I think is useful to emphasize is that oftentimes the technology we developed to do fundamental science, fundamental physics, for example, can actually be used elsewhere. So it's not just the discoveries that we make, but also the technology we developed to pursue fundamental science can often be useful elsewhere. And this is partly what happens here, where we have actually two physicists in this company who are the founders, who use technology that was developed for fundamental science, for something that's actually hopefully helping people down here on Earth, which is, I think, also a useful motivation, right? I very much enjoy studying black holes, but I'm also excited if I can do something that's more closely making a difference right now on Earth. Exactly. And this is basically that. So the idea is that some of the technology, again, that we use in this area called multi-messenger astrophysics, which is the combination of different messengers found together, analyzed together, so we can learn the most about, in this case, black holes, can also be applied elsewhere. And a somewhat similar situation happens when we are dealing with wildfires in different places on Earth. The idea is that oftentimes we only learn about the existence of wildfires once it's either too late or almost too late, when it's already getting close to inhabited communities, for example, or when they are large enough that it's really hard to stop them. So the key is, how can you use as much information you can have about them to find them as early as possible? And this is what we're focusing on here in Fire Neural Network, to be able to find wildfires as early as possible so they can be put out with much less effort and with much less harm to the environment, to humans. And one key detection we use here is lightning strikes. It turns out that a large fraction of wildfires in many parts of the world, especially the biggest ones, are initiated or ignited by lightning strikes. This is already a reason why focusing on lightning strikes is useful. But the other reason is that it's actually very straightforward to find when and where lightning strikes happen on Earth, because they produce, among other things, a very strong radio signal, just like what you detect with your phone, that can be observed from a distance. And so we can tell within seconds where exactly and when a lightning strike occurred. What we do then, when we know the direction, the position and the time, we can immediately start to look into whether this particular lightning strike could actually create a fire. We can do that by using information from the environment. If it was raining for 10 days at that location, chances are there is no fire, right? If it had been dry, but there had been, a lot of vegetation before, it's more likely that there was a fire. In addition, it turns out that lightning strikes are also not all the same. There are some that are that carry more charge, basically, and so they're more likely to create a wildfire. And so we can basically combine all this information to make a prediction early on whether that particular lightning strike created a wildfire. And so we can follow up with this either by, either ourselves. So we build a special purpose drone whose role is to fly to these locations as quickly as possible and basically take a look at, hey, is there actually fire or not? Or we can immediately inform firefighters, which is what we also do, so that they can go to the location and investigate or put out a fire if there is something. So the key is that we use all information possible, basically analogously to what we try to do with black holes, right? Combine all the information that we have available from all kinds of messengers, if you will, to make a prediction. And in this case, the key is to find this as early as possible to make the mitigation effort simpler.
Yeah, this is awesome. How else can you detect that the lightning strike that you detected actually create a fire? You mentioned it briefly, but do you use, for example, satellite image? Like, are they useful that they're providing real-time data that you can access, for example?
Yeah, so there are different kinds of satellite information. There are satellite information about, vegetation, what else is around there, which is actually useful.
So like if a lightning strike strikes maybe in an completely empty field, not really that likely, exactly. Or maybe in an urban area, not really that likely.
Yes. But now, to add to this, in principle, there are satellites that are focusing on finding fires themselves, and this is a direction. However, the difficulty is that with satellite resolutions and sensitivities, the fire has to be a certain size, which is fairly large, for the satellite to be able to see this.
And what do they see? The light of the fire?
They see the infrared radiation from the fire. Okay. But by the time it becomes strong enough that they can see it from space,
it's kind of too late, maybe for your purposes, right?
Let's say it's much later than what we can achieve down here,
exactly.
right? So it's a balance, right? You can find it at any time, but at some point the mitigation efforts will be extremely difficult and expensive.
So what fire neural networks is doing is doing the whole process from the beginning of finding where the lightning strikes is, determining whether the lightning strikes produce a high likelihood of fire. If you determine that it is, search for that actual fire. And that searching could involve all the satellite imagery, probably sensors that you have. If you can talk about the sensors, that would be cool too. But also deploying actual crafts with cameras, I imagine, to see if there's actual fire.
Yeah.
And with that, alert the authorities, hey, there's a fire. Please take care of it, kind of thing.
Yes. So starting with the detector, the first step, right? The key is that we want to learn as much about the lightning strikes as possible.
Okay.
So we deployed a network of detectors that are individually detecting the radio waves from the lightning strikes with high resolution.
Thing that we have in
it's this beauty here. Yeah. So this is one detector. And there are multiple of these at some location. And so we detect each lightning strike with multiple other detectors. That can help us reconstruct its location, properties, how much charge was transferred, and others. And this information can be used to make a prediction, again, with other information. And based on this prediction, we either send out a drone or right away inform the firefighter that this is a possible site. Please go and investigate. These are the two options. Satellites, again, eventually you can find these with satellites, but what we found is that this takes too much time. And so by the time that's there, other efforts already could find and potentially mitigate a fire. So the key next step that we are ourselves doing is a drone that can fly somewhere with basically an infrared camera and identify the fire, even if it's very small. So, as long as you can go nearby quickly, even a very small fire can be identified. Again, infrared is going to be very unique to the fire.
So the two main technical challenges that I think I'm hearing is the characterization of the lightning itself, like knowing this is harmful, like this could produce fires, and also detection of like when you determine most likely there's going to be a fire, is there an actual fire, or how big it is, I imagine, where is it, those kinds of things. Those are
yes, okay. Exactly. So again, sometimes firefighters can go directly to these lightning sites and investigate, but they have limited resources, and having one or two fire trucks drive somewhere is, first of all, slower, second of all, a lot more expensive than a drone flying somewhere. So we want to help the firefighters as much as possible, so they only go to sites where there is actually something that they have to mitigate, as opposed to just highly likely sites where they have a percentage that may not be a fire.
Right, and probably the cool thing, also like an interesting problem would be, what do you give the firefighters, right? Like, how do you create that communication?
Exactly,
like,
exactly.
Can you give them like a map of like, there's a fire in this area? That would be really cool, right? Or like, how do you send it? And maybe if there's a fire in an area that you don't contact, that you're not as close as, like maybe reaching even the fire department would be not as easy. So yeah, it's a fascinating thing. Like, if you can touch on maybe the business model, is that something that you can talk about? Like, who's your client, basically? Like, yeah.
So just we have detectors in multiple locations. Staying in Florida for a second, we work with the Florida Forest Service, who's our main partner here. Who they are responsible for many of these fires and making sure that our forests are safe. And so this is information that's available to all of them, and we're working with them to understand where we can deploy drones and where we should where we should deploy these detectors, so that we cover a certain area.
Right. That's another problem, right? Like putting the actual sensors in spots where it's important for them to be around.
So this is much easier because basically one of these detectors can monitor a distance of out to something like 20 miles. So you can draw a 20-mile radius around this. So basically you can protect all of Florida with about 30 of these detectors. So it's not a huge number. And they're also the rest of the detector is not here, but this has a solar panel and battery unit. So basically, this is a self-contained detector, which is you just put somewhere, which is not under a tree, so that you have some sunlight. But other than that, you don't need anything else. It's
right. Because Florida is like 600 miles, something like that. So like you put a bunch of them and you're good to go.
Exactly.
Right?
So it doesn't,
not really that much.
Exactly. Right? So we already cover Central Florida, and so it's something that's not as difficult to see. The sort of more important technical challenges is how you maximize the information that you get from these to inform the firefighters and make sure that they react. And also for the drone locations, right? The drone is a little different because where you fly, how you fly. So that's more, someone has to be more involved, right? The drones we're building are fully automated, so you don't have to have a human, but still you have to know where to place them. So it's a more complex decision.
Awesome. Yeah, super awesome. And we're in the office of Fire North, so that we have the device. So yeah, thank you for all of this. Final two things. We've already talked about all your physics endeavors, your company endeavors. Do you have advice for people maybe thinking about either or both, like maybe a more academic road, thinking about physics, or maybe making something useful, like starting a company? Any advice that you can give to somebody that would be interested in the things that you're doing, for example? Yeah,
so there are two different things to some extent. I would say for my academic role, if you will, I think the key is, especially when I tell every student that I have the opportunity to do that what you have to prepare for is research. Research is going to be the key work that's, or the key differentiator in how successful somebody is. And you can only learn to do research if you do research.
Yes.
So classes are very useful for many reasons, but you need hands-on experience with some research. So my recommendation is that you should forget about summers as vacation time,
right,
and you should
get
think
to
of them
work.
as a great opportunity to do internships. And for the startup part or the company part, I think this is also and I'm learning as I'm getting involved in this direction. It's also its own field. It's also its own sort of little environment. And so I think here too, getting hands-on experience with being a part of one of these startups or one of these efforts can be extremely useful. And then you learn the ropes. You learn how this works. And again, it works very differently than other endeavors I've tried before. So this is also there's a very interesting learning curve, and the best way to do it is to actually do it.
To actually do it.
Yeah. So my recommendation is get out there and get involved in one of these.
Final thing, Dr. Bartos, what are you grateful for?
I think for many of these things, it's a group effort, right? So there's so much you can do, right? Just me doing these or being involved in these two things shows how limited time and energy I have for these. So I think the most important thing in these successes and what I'm really grateful for is the people I'm working with, both in my academic role and here at FNN. And I think that's multiplies not just how fast we can proceed with research or the company, but it also makes things a lot more fun. So I'm really grateful for my partners in both of these. Oftentimes, the technology we developed to do fundamental science, fundamental physics, for example, there's not just directly just the discoveries that we make, but also the technology we developed to pursue fundamental science can often be useful elsewhere.